At present, the EV industry is keeping fast increase. Slow charging, as the main charging scenario, mainly relies on the onboard charger, OBC. Its performance, protection and stability are crucial to the actual user experience and charging quality. Here I will test an OBC from T. The perspective of grid adaptability and protection with the help of professional test instruments. In this video, we will demonstrate the test of the OBC. The test instrument I use is the ITECH IT7900 Regenerative Grid Simulator. The IT7900 is capable of meeting all standard OBC tests, and it can protect the OBC, even if the OBC protection circuit is not perfect. IT7900 can be used as an AC power supply for applications such as power supplies containing PFC circuits, inverters, and other test scenarios. It also can simulate the power grid and be applied to the T. A state of PV inverters, OBCs V2G and so on. This is the test topology. It mainly shows interval PFC plus CLLC. The PFC rectifies the AC to 800 VDC through a circuit breaker. It then converts it to a wider range, 204 V DC through the CLLC topology to power supplied to a high voltage battery pack. Op power full load, 72 kW. AC input, 85-285 frequency, 4100 Hz. Max. Input current, 32 output voltage, 204 V. In the current EV development, it requires PF 0.9, full load efficiency, 94%. To evaluate whether the AC power supply can meet the input range of the OBC. OBC full load operation test stack power supply protection for OBC input over voltage and input over current. How to test the PF of OBC at different input frequency. Show to test the efficiency of OBC at different input voltages. How to protect the AC power supply itself in case of input short circuit. The IT7900's AC voltage and frequency range can cover the OBC's input range. This test is used to verify that the input range of the AC power supply can cover the input range of the OBC. It also teaches how to set the voltage and the frequency. As mentioned before, the input range of OBC is 85-285 VAC, the frequency is 2100 Hz. Turn on the IT7900 by the knob, and you can see it in the power on initialization through the LCD screen. Initialization is done and it powered on. Here you can set the output voltage and frequency. IT7900 provides a touch screen. The cursor shows the voltage can be set. The minimum and maximum voltage can be entered by pressing the key and enter to confirm it. The input voltage of the OBC is 85-285 VAC, and the input frequency is 2100 Hz. Click on the frequency value in the upper right corner, enter the frequency you want, and press enter to confirm it. In the second way, we can adjust the voltage and frequency through the knob. The cursor flashes at the 10th digit. Rotate the knob to modify the 10th digit of the voltage value, and press the right button once to edit its individual digit. Of course, the knob can adjust the frequency in the same way as just adjusting the voltage value. Obviously, the output range of the IT7900 is wide enough to completely cover the input range of the OBC. The OBC achieves full load at different input voltages. This test is divided into two parts. 1. The ability to output rated power at both the minimum and maximum input voltage. 2. Can maintain a maximum input current of 3-2A at full output under different input voltages. The test environment is built as shown in the video. The output L and N lines of the AC power supply are connected to the input of the OBC. The output of the OBC is connected to the high voltage DC load. The OBC is powered by a 12V KL30 Simulate 12V battery. The PC software communicates with the OBC by CAN to power it on remotely. Now start the low voltage and high voltage startup experiments. We first verify the low voltage startup by setting the voltage value as 85V and outputting it. According to the requirement, the OBC needs to be able to output power up to 1500W at 85V input. Send the power on command to the OBC and wait for it to start. At this time, the AC power supply shows that the current is about 17A and the operating power is about 1500W, so the 85V low voltage startup experiment is successful. Next, we verify the high voltage start. Click Set, enter 285V through the keyboard, press Enter to confirm, then click on to Output. In this condition, the OBC needs to be able to output 7200W at full load. Send the power on command to the OBC, and load it to full load. In the AC power supply interface we can see that the input current of the OBC is about 26A. At this point, the full load output is about 7200W, which proves to pass the 285V high voltage startup test. The AC power supply can also monitor its output through its own waveform function. Clicking on the waveform, you can see the voltage and current waveforms. The interface can also display the parameters in real time. The waveforms can be saved and exported to play back the test process, a feature that helps developers to analyze the data. From the above tests, we can conclude that the OBC can output a given power under both high and low voltage input conditions. Next, we add the operation of the load side of the OBC, and this test uses the ITECH high voltage DC load. We put it in CV mode, that is constant voltage mode, to simulate the energy absorbed by the battery pack. At this time, the OBC output is 360V. Send the power on command to the OBC, and set the full load output. At this time, the interface shows that the output current is about 20A and the output power is about 7200W. Next, let's have a full load operation test at different input voltages. In the first condition, we set 180V, 60 Hz, set the parameters and press output. Send the power on command to the OBC, and the OBC is then powered on. The current in the main interface can monitor its operating conditions. At this time, it passed the test. We can directly set the voltage of the IT7900, and then switch the operating conditions after confirmation. The next condition input requires 200V, 60 Hz. Send the command to turn on the OBC. The current display in the main interface is about 32A, and the OBC outputs at full load. The next input is 220V, 60 Hz. Input voltage, press Enter to confirm, send command, and turn on the OBC. The current display in the main interface is about 32A, and the OBC output at full load. The last input requirement is 230V, 60 Hz, and it sets the output voltage to 230V. The OBC needs to output 7200W under this condition due to the input voltage rise. Send the command to turn on the OBC. At this time, the interface shows that the current reaches 32A, and the OBC outputs the maximum power of 7200W at this time. The above experiment shows that the OBC can output at full load under different input voltages. This further verifies that the ITECH IT7900 can meet the full load debugging requirements of the OBC under different output voltages. Protection of OBC input over voltage and input over current. This topic requires verification that the ITECH IT7900 can protect the OBC from overvoltage and overcurrent. This protection can ensure the safety of the DUT in the pre-development stage, when the hardware protection of the product is not perfect. The following is a test demonstration of the maximum input voltage of 285 V and the maximum input current of 32A for the OBC. Here we conduct the experiment of overvoltage protection. Press CT or L plus config to enter the protection setting interface. The voltage RMS protection is shown here. The maximum input voltage of the input OBC is 285 V. The delay time is set to 0.1 seconds. The parameters can all be set by the knob Enter for confirmation. Back to the main interface, set the output voltage 290 V, and confirm output, then it will immediately enter the overvoltage protection mode. The output will be terminated and the buzzer will sound. Exit the protection mode through by Shift plus ESC, and the overvoltage protection experiment is completed. The following demonstrates the OBC full load overcurrent protection. Enter the protection setting interface. The maximum current limit of OBC AC side is 32A, set the effective value to 32A here. The second column is the trigger time setting, and the trigger time is set to 0.5 seconds. The third column is the protection type. Touch and press Enter to see two options. They are limit and disable. Select trigger protection, stop output and disable. Go back to the main menu. The above is a demonstration of how to set the overcurrent protection. Let's switch the camera to the distant view to verify whether the AC power supply can trigger overcurrent protection when the OBC is fully loaded. According to the demonstration, set the current RMS value, protection delay time and protection mode. After the AC power supply output, send the power on command to the OBC and keep loading. When the load reaches 32A, the AC power supply stops outputting, and the buzzer sounds. Exit the protection mode by combining the keys Shift plus ESC, and the overcurrent protection experiment is completed. The experiments of overvoltage protection and overcurrent protection are completed. The experimental results are passed. In the actual debugging process, when the internal overvoltage and overcurrent protection of the object to be tested is not done perfectly, the developer can only protect the object to be tested by testing the power supply, or the load limit. As you can see from the operation just now, the protection of this AC source is relatively easy to set up, and all the protection parameters can be completed in the same interface. So the function of this AC power supply fully meets the debugging needs of OBC. The performance of OBC at different frequencies. In this part 1 will demonstrate how to test the performance of the OBCs. PF value plays an important role in the power quality of the grid. That's why car manufacturers focus on asking developers to improve the PF value during product certification. In this development phase, the product is required to have a PF value greater than 0.9 at 40 Hz 100 Hz. We take the degree of 10 Hz, test, the PF under different working conditions. In the test we added power analyzer to calculate the PF value of input AC. Now we conduct the test of the value at different frequencies. According to the previous introduction, to set up the test environment, the first condition is 40 Hz full load output. Set the AC power supply to 230V, 40 Hz and confirm the output. Send the power on command to the OBC, and increase the power to full load. The data from the power analyzer shows a minimum frequency of 40 Hz, and a PF of 0.9935 at full load. Turn off the OBC output. Let's do the next condition test with a 10 Hz increase in frequency. At this point in the AC power supply's frequency setting screen, just enter 50 directly and confirm. After setting, turn on the OBC to full load. At this time, the PF value at 50 Hz is 0.9958. The PF at 60 Hz is 0.9927. The PF at 70 Hz is 0.9790. The PF at 80 Hz is 0.9846. The PF at 90 Hz is 0.9802. The highest PF value at 100 Hz is 0.9732. The test shows that this AC power supply has stable output at full load at different frequencies. Efficiency of OBC with different output voltages. In this topic I will demonstrate how to test the efficiency of OBC. The OBC contains a resonant circuit with a wide voltage output range and a high efficiency at each operating point. As before, we need to set up the power analyzer, read the input voltage and current, output voltage and current, and calculate the efficiency. The test condition is the full voltage output range 200-480V, and the test scale is one set of data every 20V. Now the OBC full load efficiency test for different output voltages. The AC power supply is set at 230V, 60 Hz output. The power analyzer shows the input voltage here, and the efficiency of the OBC below. The first working condition is 200V output. The OBC is turned on and reaches full load. You can see the efficiency of 91.4%. The next working condition is 220V output. We just need to increase the constant voltage output of the electronic load by 20V. Again, send the power on command to OBC. Output 220V, full load OBC efficiency is 92.2%. 240V full load OBC efficiency is 92.8%. The 60V full load OBC efficiency is 93.3%. The 280V full load OBC efficiency is 93.5%. The 300V full load OBC efficiency is 94%. 320V full load OBC efficiency is 94.4%. Three 40V full load OBC efficiency is 94.8%. 360V full load OBC efficiency is 94.5%. 380V full load OBC efficiency is 94.6%. 400V full load OBC efficiency is 94.7%. 420V full load OBC efficiency is 94.3%. 440V full load OBC efficiency is 93.7%. 460V full load OBC efficiency is 93.6%. The last working condition has the highest output of 480V full load, and the OBC efficiency is 93.6%. At this point, the efficiency test experiment is over. The output voltage is near the resonance point, the highest efficiency AC power supply output short circuit protection. In the OBC commissioning stage, the PFC circuit, if a short circuit occurs, then it will be directly from the high current. This situation is dangerous for the AC member. We can set the current over current protection to avoid this situation. When triggered to the threshold value, it can stop the output of AC power supply in time to minimize the loss. We connect a blanket in series between the output of the AC power supply, that is, the input of the OBC, to simulate a short circuit by closing the blanket. After setting up the test environment according to the schematic, we conduct the experiment of input short circuit to the OBC. Because it is a short circuit under full load, there is a risk of damage, so you need to set the protection value of the AC power supply. Release the current RMS threshold to 50A, and set the protection on when the current peak is 80A. After setting the protection value, go back to the main interface and set the output voltage and frequency to 230V, 60 Hz. After setting the parameters, confirm the output AC power, and turn on the OBC to load to full load. On the interface we see that the power reaches full load. Shut down the breaker to simulate a short circuit. After it, the AC power supply immediately stops output, the buzzer alarm, and the short circuit experiment is successful. Thanks for watching, and see you next time.